Okay, so today we want to look at propositional logic. Okay. So, to keep things into perspective, our motivation for studying logic is to be able to make inferences. So, in general, if you are given a set of facts and if you are asked a statement about which is not in this set, some statement, and we are asked the question, is this statement true or not true, then we should be able to answer that question, and we want to build a mechanism or a machinery to do this automatically or mechanically, if not necessarily automatically. By mechanically, we mean by applying a set of rules which can be done by a human as well. So, whenever we talk about a logic, we have first talk about the language part, which like any formal language is a set of sentences that belongs to this language. So, what is the language of propositional logic? It has two components. One is called the logical part, and it essentially contains the alphabet of these operators or operator symbols. So, you must keep in mind that we want to distinguish between the syntax of the language and the semantics of the language, and we will not do so very pedantically in these lectures, but we need to distinguish between the fact the syntax part which says that these are just some symbols that we use, but of course, the meaning of these symbols comes from the semantics, and which, as you are familiar with, is given by the truth tables that we can construct for each of these operators. So, at one level or the syntactic level, we will just treat them as symbols, but when we talk about the semantics of sentences, then we will sort of revert to the idea which comes from the truth table essentially. So, for the moment we are focusing only on the syntax part, just think of them only as symbols essentially. Then there are other things like brackets that we can use. Then there is the non-logical part. By this we mean it varies from problem to problem essentially. Let us just assume that this is here. So, we have symbols which is set of proposition symbols. So, this is the alphabet with which we construct the language. We have a constant set which we use in all propositional logics, and we have a varying set which may be in principle infinite or at least countably infinite, or it could be finite as well. Essentially, we may be just talking about a few statements P, Q, R, S, T, then this set will be a simple set of statements. So, this is a countable set of propositional symbols. Okay. We have two more symbols here. One is, I will use this notation, but you could also use F or 0, and the other is this, but you could also use T or 1 or even true and false, the full letters, it does not matter. Basically, these are these two symbols which are there in all logics. This we often read as bottom, and this we read as top essentially. Bottom or false or 0 are equivalent. Basically, it is a set of two symbols, it is a two valued logic that we are talking about, and when we talk about the semantics, then every sentence in our language will be mapped to one of these two symbols, and that is how the semantics would be defined. One, we would implicitly between us say that it stands for true sentences and the other stands for false sentences. I mean, this is false sentences and this is true sentences, but that is only for us, our sake. As far as the logic itself is concerned, the machinery itself is concerned, these are just two symbols to which sentences are mapped onto essentially. But it always helps to keep in mind the semantics, which is that we are talking about false or true statements. What is this machinery that we are talking about? This machinery that we want to build is essentially a machinery which first defines this language and then tries to reach to sentences in this language essentially, and a mapping for to this. Anyway, we will come to that in a moment. So, the set of sentences let us call it SP, where P stands for propositional logic, is defined as follows, that this belongs to this set, top belongs to this set. So, that of course, you know they stand for something which is always true and something which is always false. So, this is a set of propositional symbols, let us call this set P. Then we say that if alpha belongs to P, then alpha belongs to SP. So, every propositional symbol is a sentence, and then we say that if alpha beta belong to P. So, alpha beta, these Greek symbols we will use as variables to stand for any sentence essentially. If alpha and beta belong to SP and is a binary operator symbol. So, of these symbols we will distinguish between binary and unary, and we will not talk about higher order operators, and you do not need to. So, this one is unary. We often always also use this sign for this. For this sign we also use sometimes an arrow. For this we sometimes use two arrows, and there are other symbols which we have not mentioned here, but we can build a language using other symbols. So, you are probably familiar that there are 16 possible binary operators that you can devise, and these are only 1, 2, 3, 4 of them, and there are 12 more which. So, if alpha beta belong to the set of sentences, and so instead of using this particular symbol, let me just use some abstract symbol which says this is a binary operator symbol, then alpha belongs to a set. So, we are just defining the language here. So, for example, if P and Q are two propositional symbols, then P and Q belongs to this set, and once this belongs to the set, we can also say P and Q or Q belongs to this set. So, essentially we can combine this any number of times, and we can create sentences which are arbitrarily long. So, an infinite set of sentences in fact we can create, even if the set of propositional symbols is finite essentially. Likewise, we have for the unary symbol, if alpha belongs to SP, and we will just use this symbol is a unary operator, then so essentially now we have defined, we started with a set of propositional symbols, and we have augmented this with more sentences, and the sentences are using the operators, so or the connectives essentially, and the bracket symbols and this. So, we can get an infinite set of symbols. So, this is a syntax. What is the meaning of these sentences? Propositional logic is not concerned with meaning. Okay. So, the meaning is given by us essentially. So, I can say that if I have a set of sentences like Alice likes math and physics, and I call this sentence P, that is only for my own sake essentially. I want to, let us say, reason about Alice, and I create a set of sentences about Alice. So, I say Alice likes maths and physics, Alex likes music, if Alice likes math, then Alex likes algebra, if Alice likes algebra, and music. So, I should really say Alice likes music, then Alice goes to college. Let us say I have this set of sentences. So, I am just trying to give you a flavor of, and you are probably anyway familiar with this sort of a thing, the kind of things we can do with propositional logic, and from this we want to ask the question that is this sentence so is this sentence can it be inferred or not essentially. So, I can now encode this problem in propositional logic, and I can say that Alice like maths is P and Alice likes physics is Q, then I can call this sentence as P and Q, because Alice likes maths and Alice likes physics. This I can call as M, and then I have a statement, if Alice likes maths, then Alice likes algebra. So, this sentence I can call as A, let us say, and this whole sentence I will represent as M implies A, and this sentence says Alice likes algebra, Alice likes music, P implies A. If Alice likes music and then Alice goes to college, so this let us call it C. So, this sentence I can write as A and M implies C. So, ideally I should put brackets around here, but I am not doing it because when it is clear then we do not often put brackets, and this is a sentence C, and we are asking whether this sentence is true or not. So, I am saying here that M means that Alice likes music, but that is only between us. As far as the logical machinery is concerned, it is not concerned with this at all. So, like we said, logic is formal essentially. We say logic is it only depends upon the form of the reasoning. So, essentially what we are going to ask is that if I assume this is true, this is true, this is true, this is true, then is this necessarily true. So, remember we said logic talks about deduction essentially, but suddenly we have started talking about truth statements. So, let us talk about truth first. When we say semantics, we essentially have two kinds of, what should I say, flavors to it. One is as to what does the sentence mean, what does P mean, what does Q mean, what does M mean. Now, we are saying that logic is not concerned with that essentially. The other thing is truth values, or some people use the term truth functional semantics. And what we are saying here is that there is a mapping called val, which goes from this set of sentence SP to the set we want to define this mapping, and remember that those two symbols, we said that between us we will assume they stand for false and truth essentially. So, what is the mapping we are looking for? We are looking for a mapping which takes an input any sentence in my language and maps it to one of those two symbols, which means it tells me whether this, that is again between us, whether the sentence is true or false essentially. So, we have to define this mapping. So, we start with a function V which maps this set P to the set O. That is external. What do I mean by this? Somebody is telling me what is true and what is not true, that I am saying that Alice likes music. So, I am mapping M to true, I am mapping P to true, Q to true, and so on and so forth. So, in general, given a mapping of the propositional sentences, we can derive a mapping of this thing. So, this is a general notion, we will come to specifics later. Sometimes you have uncertain knowledge. So, I might say P is true or R is true, in which case of course, I am not given the mapping, but I am given the mapping for P and R is true. So, we will come to that a bit later. First, we want to define that if we are given a mapping which we call V, which takes you from the set of propositional symbols to this, then can we define this value function, and that we can do as follows. If alpha belongs to pi, then val alpha equal to V alpha. Because somebody has given us what it maps to. We are really talking about truth tables from this point onwards. Then we always define val is equal to this thing and val there is a little bit of overloading happening here. Ideally, I should use different symbols here essentially. So let us say we define it to 2. So now what I am really saying is that this bottom symbol always maps to the truth value false. So let us call this is a set of truth values, and we are working with a binary 2 valued logic. So there are these two truth values, which one we call false and one we call true, and bottom always maps to false and top always maps to T, which stands for true essentially. And then if val alpha is equal to true, then val not alpha is equal to false. So, I write rules like this: if alpha maps to true, and alpha is a sentence in my language there, then the another sentence in which I have prefixed alpha with this unary operator. So, we will of course, between us read it as not alpha, then not alpha maps to f, and like this we can write other rules. So, for example, you can say if val alpha is equal to true and val beta is equal to false, then val alpha implies beta equal to false. So, you are familiar with this. So, we will not spend our time writing this. Essentially, you can convert these kind of statements into a truth table. So, for example, alpha beta alpha implies beta. So, false false true true false true. Well, I do not know whether you can make out between my f and my t. Maybe I should have chosen 0 and 1, but anyway, you know the truth table for implication. So, this is a truth table for implication. Instead of simplification, if I can write it like this, for each row I can write a sentence like this. So, this stands for the third row here. This statement corresponds to the third row. So, I can construct a truth table, or I can write statements like this and so on, but we are familiar with this as to how to define the semantics of, how to lift the semantics of simple sentences to compound sentences when they are made up using operators, and we have these logic rules that we are all familiar with essentially. Okay, so, what have we done? We have said that we have defined the language of propositional logic. We have defined what is the set of sentences which make up this propositional logic, and then we have defined a mapping which tells us that if we knew the truth values of the constituent sentences, how can we lift those truth values to more compound sentences, and we have rules for doing that. Which means that if somebody gives us this valuation which says that okay, these are the 5 atomic sentences or propositional symbols, and they map to true, false, respectively. Then for this entire set of infinite formulas, I have a mechanism for determining whether they map to true or whether they map to false, and that I can do by using truth tables or something like that. So, where does the logic machinery come in here? The logic machinery comes in. The logic machinery, as we said, deals only with the form. It does not deal with content, it does not deal with semantics, it does not deal with meaning. What we are interested in is, can we develop a syntactic machinery which will do that mapping for us. Instead of having to apply these rules repeatedly, recursively you can keep applying the rules. If some formula alpha and some formula beta, what is the truth value of this? It depends on, if both of them are true, then this compound formula is true, and you can recursively you can break down essentially. Instead of doing that, instead of having to construct a truth table, can we have an alternate mechanism for doing that? Okay. So, to come to that, let us say that somebody has given us this function v, which basically says which atomic propositions are true and which are false. From that we can compute this function val, which says the same thing for compound sentences, and from that we can define this set T is a set of true sentences. So, of all the sentences which I can construct in my language, the semantics tells me which are true and which are false, but I want an alternate ways of reaching those sentences. I do not want to apply these rules, I do not want to construct truth tables. Why? Because the size of the truth table can grow to be very large essentially. I have two constituents here, alpha and beta, and I have four rows in my truth table. If I had a sentence like alpha and beta implies gamma or delta implies theta, then I have 5 variables and I would have 2 raised to 5 rows in my truth table. So, the size of the truth table grows exponentially with the number of propositional variables that I use in my sentence essentially. So, I do not want to construct a truth table. What do? We define instead the notion of a rule of inference. So, let me rub this part out. So, what are we interested in? We are interested in reaching that set of true sentences, and what do I mean by that? That if somebody has given me the premises which is this set P that I had talked about, the semantics defines this set T. Premises I assume to be true. So, these I assume to be true, but from if I assume these to be true, then there is a whole set which is true. So, for example, I can say M or not Q, is this true or not? So, there is an infinite set of sentences I can construct using these symbols, and I can ask a question of each of them whether that is true or not. From that I can collect the true sentences and I have this set true essentially. Now, we are asking that is there a mechanism of reaching this set again through a different means. So, now we are talking about the logic machine, or you can say an inference. This uses something called rules of inference. So, what is the rule of inference? The rule of inference is a pattern, and the most popular one that no doubt you are familiar with is called modus ponens, and modus ponens says that if you can see a sentence alpha, and this sentence belongs to the set of sentences that we have, and if you can see a sentence alpha implies beta, then you can add the sentence beta. What do I mean by this? That if I have a set of sentences given to me, a set of premises for example, or a database of sentences if you want to use that term, then I can keep adding new sentences to the database essentially. And how do I do that? I do it by this pattern matching mechanism, which says that if I have alpha and if I have alpha implies beta, then I can add beta essentially. So, this is one rule of inference. There are many others you must be familiar with. So, one rule is called simplification, which we will need for this. It says if you can see a sentence of this kind, then you can write a sentence of this kind alpha. So, notice that once we have rules like simplification, we do not feel compelled for somebody to give us the set of all atomic valuations for all atomic propositions. So, somebody has given us here P and Q. From this, by applying this, we can always add Q to or P to the set. When we say we can add this new sentence beta or we can add this new sentence alpha to our database, we also use a term that we can derive beta essentially, or we also use the term prove beta essentially. So, if alpha is given to us and alpha implies beta is given to us, then we can say we can derive beta or we can prove that beta is true essentially. So, the notion of a proof is distinct from the notion of truth that we are talking about there. The notion of truth is based on the semantics of the operators that we have defined. What does it, what does and mean, what does or mean, what does implication mean, what does negation mean, and when we say mean, basically we are talking about the truth table essentially. How does and combine the truth values of its component to give you a new truth value? That is the meaning of those operators. And truth, the notion of truth is based on the notion of semantics of those operators essentially. The notion of proof or derivation is a purely syntactic notion. It is purely based on pattern matching. It says if you can see such a pattern and if you can see such a pattern, then you can derive this pattern. It has nothing to do, at least on the surface, with the notion of truth essentially. Ideally, of course, we would not be interested in a machine like this, a syntactic machine like this, which is producing something which we are not interested in, and we are interested in true statements. We want to know what is true, given some premises, what else is true. So, theorem proving is the name that we use for this essentially. So, let us see what is happening here before we look at the machinery further. What has been given to us is P and Q. So, let us label number this now. 2 is M, and you are familiar with this process. P implies A, 4 A and M implies C. These are the 4 facts, is a term sometimes we use, given to us that these 4 sentences are true. Then the conclusion that we are interested in is C. Is C true or not? Will Alice go to college or not essentially? But we are not looking at the meaning of these sentences anymore. We are not even looking at the truth values of the sentences. We are asking that will this machinery that we have talked about 2 rules of inferences, there are more rules that we can talk about, and if necessary we will introduce them. Can we have this machinery produce this formula C or derive this formula C or prove this formula C? So, what is this machinery, this logic machine? Essentially says pick a rule and corresponding data. By data we mean the sentences which are already there. So, for example, these sentences are already given to us essentially, and if some rule is applicable to this data, take that rule and take the data and add consequent of rule. Of course, there is a matching component that I am sort of not stating explicitly here. What is the consequent? The consequent is written below the line here, written below the line here. We also use another way of signifying this rule. We say alpha implies beta. That is another way of writing this rule, which says that given alpha and given alpha implies beta, you can derive beta. So, this symbol is used for proving or deriving thing, and this is stating a rule of inference modus ponens. It says that if you are given these 2, you can add that essentially. Corresponding to this notion of proof is also the notion of truth. then we are asking if this is true and this is true and this is true and this is true, then is it necessary that C is true? We would write this as follows: P and Q and M and P implies A, and this one A and M implies C. We have, so corresponding to the semantics of sentences, we have this notion of truth value, and corresponding to the notion of truth value, we are saying that these 4 sentences entail C. So, the premises, what are the premises? These 4 things given to us. Premises entail the sentence C, and that more formally we write it like this. This is the first premise, second premise, third premise, fourth premise, and that this similar symbol, but with 2 lines, is for entailment. And entailment says that if these are true, then that is necessarily true, that you cannot escape the fact that that is true. That is the notion of entailment. So, that is a set of true sentences that we talked about, and entailment basically asks the question, does this C belong to those set of true sentences or not? Do these premises entail C? The question we are asking here is, can we derive C from the premises? To derive C, we have to use these rules of inference. For entailment, we have to use the truth table for the operators. They are quite distinct. So, I am sort of, that is why I am emphasizing the fact that they are different. So, our logic machinery basically says pick a rule and corresponding data and add consequent of the rule, and we put this in a loop essentially, and what this will produce is another set of formulas, which we will call as what should I call this? Let me see, because I have used the symbol P earlier. Let us say this is PR or something, some symbol. What is this set? This is a set of, I should write it here, set of provable formulas. Okay, so I have inadvertently sort of switched to the terminology of formulas, but essentially a formula is a sentence in my language essentially, a well formed formula. So, it is a short form well formed formula. Anything that I can construct using the syntax that I have defined is a formula, and this set PR is a set of all those formulas which are provable given the set of premises and the set of rules of inferences that are given to me essentially. So, the question we are asking is, does C belong to this set or not, and instead of writing this loop which will keep going indefinitely because the set is actually infinite, we can put a termination criteria that if C, if the consequent equal to C, then stop essentially, we can just put in a condition there. So, that means we are writing a program to generate a proof for only C and not worrying about other provable formulas essentially. So, that is a small variation essentially. So, how do we go about this? This is given to us. We can add P here. Why? Because there is a rule called simplification, which says if you have alpha and beta, and alpha matches P and beta matches Q. So, therefore, I can produce P here by simplification. There is another rule. So, I can use now mode exponents, because I have P and I have P implies A, I can add A. Remember, mode exponent says if you have alpha, alpha is P and alpha implies beta is P implies A. So, therefore, I can beta becomes A and I can add A. There is another rule which says that if I have 2 things, then the conjunction of those things can be added, which is called addition, but so I can write AM because I have A and I have M, I can write A and M, I can add this. This is another rule of inference which I have not written here explicitly. And then again I can use modus ponens. So, ideally I should say, how did I get this? I got it from 1 and simplification. How did I get this? I got this from 5 and 3 and modus ponens and so on essentially. So, you are familiar with this process, having studied geometry and algebra in school. So, now I have got AM, I got this by addition of A and M, and then the last thing is C, because I have this A and M matches alpha and A and M implies C matches alpha implies beta. So, C matches beta. So, I can infer C using modus ponens. So, this is a syntactic machinery of arriving at a proof of C, which does not look at the meaning of the operators. It does not understand what does AND stand for, what does implication stand for, all it has is a set of rules of inference which says if you see this pattern and you see this pattern, you can add a new formula to your database, and we can put this into a cycle and say can we add C. So, at this point we have added C. So, we can say yes, C is provable into this thing. So, that is a notion of proof, notion of provability. That is a syntactic machinery we are after, because it is easy to write pattern matching algorithms, and in this case the patterns are exact. So, the matching is not even hard, and you can keep looking for rules and matching data and keep producing new data. So, you can imagine a forward search algorithm which says this is what is given to me, this is a rule available to me, from this and this I can infer this, from this and this I can infer this, from this and something else I can infer this. So, I can keep moving forward, and that C is somewhere. So, if I can reach this formula C, then I have stopped. So, the forward state space search that we talked about is essentially being done here in some way. So, notice that we have said pick a rule, we have not said which rule. That of course, is a very tricky question. You can go off in some direction and infer meaningless things. So, that is obviously the thing that we need to tackle next essentially. Okay. So, what have we done? We have defined the language of propositional logic, the syntax, then the semantics, the truth function semantics, which says that given a sentence we can arrive at its truth value using the truth table approach. Then we talked about this machinery of making inferences, which does not look at the semantics, but it only looks at the syntax. It is a syntactic machinery and basically adds new formulas to that. We can sort of build a machinery to produce a formula. So, is this machinery a good machinery or not? This is a question which is asked by all logicians. Okay. So, what do we have? We have a logic machinery. Is this logic machinery doing what we want it to do? So, there are two notions that we use here. One is the notion of soundness. The notion of soundness says that my machinery will only produce true formulas. We can express this as follows. If so, let us say L is a language given to us or set of premises given to us. If L entail alpha, then if L derives alpha, then L entails alpha. The notion of soundness says that my logic machinery will produce only true formulas. If it produces a formula, then that formula must be true. Of course, trivially, if your logic machinery does not produce any formulas, it will be a sound machine, but that of course is not a very good machinery. The other property is completeness. That we have already spoken about. It says that if L entails alpha, then L derives alpha. Completeness says that if a formula is true, then there is a derivation for the formula in my logic machinery. That if I had a non-deterministic machine which knew which rule to pick and which data to apply to, it would produce a derivation essentially. Of course, in the absence of having non-determinism, we have to use search, and we will sort of focus on that as we go along. Tied to soundness is a notion which is basically is derived from soundness, but it is useful to talk about it. It is consistency. Consistency says that a logic is consistent if you can derive either alpha or negation of alpha, but never both essentially. So, consistency says that L derives alpha and I must use the exclusive or L derives negation of alpha. So, this stands for exclusive or, which is not a symbol I have defined here, but we can define it in terms of this. So, consistency is basically tied up to soundness. As if you just think about this a little bit, only one of those things will be true, and soundness says that I can prove only those true things essentially. If I prove something, it must be true. So, you cannot have alpha and not alpha being derived. So, which is basically the other side of soundness, but very often we talk about consistency. So, soundness, completeness and consistency. So, when we begin the next class, we will talk about these properties. We will ask the question, when is my system going to be sound? Why is this rule sound? How do I say that this rule is sound? So, we will ask this question. We will also talk about completeness a little bit, but we will not prove the completeness properties. The proofs are simply a little bit longer, and then we will move on to higher order logics essentially. Maybe I will give you an example of logical systems which were known as axiomatic systems. So, last 200 years mathematicians have been talking about building axiomatic systems. So, they have been saying if you use this set of operators and this rule of inference, then your logic machinery is complete essentially. So, I will just give you an example. We will not prove their completeness, but we can talk about it essentially. So, in the next class we will begin with soundness and completeness, and then move on to first order logic eventually. We will also focus on this machinery as to what really this algorithm should be essentially. This seems too vague and it needs all this power of non-determinism to work. We need something more efficient to be able to derive the proofs essentially. Observe that, of course, we are not talking about first order logic here, but in first order logic you would have this problem. You could say if a number is odd, then its successor is even essentially, and if somebody tells you 5 is odd, then you will say go into a direction saying 6 is even, 7 is odd, 8 is even. Of course, you have to have the other rule also, that if a number is even, then its successor is odd. Then you will just keep making statements, 5 is odd, 6 is even, 7 is odd, 8 is even, 9 is odd, and you will never come out of that loop essentially. So, obviously, that is like depth first search going into an infinite branch. That danger lurks even in this algorithm here, and we will have to look at some of those issues. So, we will stop here.